Kenexis Consulting Corporation. Our key capabilities using a lifecycle approach to safety and security. We do process hazard analysis, safety instrumented systems, fire and gas systems, alarm systems, relief systems, and cybersecurity. My name is Christopher Weil. I'm a senior consultant here with Kenexis Consulting Corporation. 28 years of experience. I've been an ISA chair member for quite a few years, and I have a patent for the control of pressurized micro-channel processes. This was a development from a Battelle Research spin-off company. So our webinar today is going to be about safety requirement specifications. The topics we're going to discuss, so we're going to discuss a short safety lifecycle review, the SRS Safety Requirement Specification Definition, and of course the SIS Safety Requirements, and the applicable standards of ISA 84 IEC 61511, and some mention of 61508. Safety lifecycle is the beginning of the safety system from the starting at the conceptual phase of a project and finishes when all of the safety instrumented functions are no longer used. It starts out with the conceptual design and ends up when the facility is either shut down, mothballed, or taken permanently out of service. No need for the safety equipment to be functioning any longer. Safety life cycle, as identified in IEC 61508, Part 1, Clause 5.2.6. The documentation shall be accurate and concise, be easy to understand by those persons having to make use of it, suit the purpose for which it was intended, and be accessible and maintainable. This is a very key factor of the safety life cycle. We'll see as we proceed through the presentation that a lot of documents and a lot of information is used to develop your safety instrumented system and to determine the requirements of the safety instrumented system. And these documents must be accessible, maintainable, and most of all, easy to interpret. The SRS Definition and Purpose, ISA 84, which is IEC 61511 modified, Part 1, Clause 10.2.1, the safety requirement shall be derived from the allocation of safety instrumented functions and from those requirements identified during safety planning. And again, it states here that they need to be clear, precise, maintainable, written to aid comprehension by those who are likely to utilize the information at any phase of the life cycle. So that is, no matter what type of document is being produced, be it the PHA, the process hazards analysis, the LOPA, the layer of protection analysis, the SIL selection, the safety integrity level selection for the safety integrity or safety instrumented functions, this documentation should be done in a very clear and definable way that makes it easy for a layman to understand, such as the instrument tech who has to go out into the field and maintain this. He's probably not going to understand short abbreviated lingo of a PHA, so these documents, when they're produced, should be produced in a fashion that gives clear and concise information that's understandable by laymen. SIS Safety Requirements, again, ISA 84. These requirements shall be sufficient to design the SIS and include the following. There are 27 items that are required by Part 1, Clause 10.3.1. This webinar will cover several of the topics with examples and give an example of how to bring all of this information, which is in various independent documents, together. So we have a description of all of the safety instrumented functions necessary to achieve the required functional safety. That's a description of the SIPs. That's the high pressure in the fuel gas system causes a shutdown of your fired heater. Requirements to identify and take account of the common cause failures. This is the scenario where maybe two transmitters are on the same tap and that tap gets plugged. We can have a common cause failure of those transmitters, a single point of failure. A definition for the safe process, state of the process for each defined safety instrumented function. The safety instrumented function is going to take an action to put the process into a safe state. In our fired heater, it's going to close the gas valves. So that definition needs to be clear and concise. A definition of any individually safe process states when occurring concurrently create a separate hazard. This is common in a power outage and where all your processes go to a safe state. Your fail closed valves fail closed, and what happens then is you put an excessive load on the flaring system. These are the types of things that need to be looked at and evaluated, particularly if one safety instrumented function, such as the downstream vessel on a liquid leg out of another vessel, would shut down. It might present a high-level hazard to the upstream vessel. Then we have the assumed sources of demand and demand rate on the safety instrumented function. This is how many times has this entity tripped in the past? How often is a demand placed on the safety system? I've seen instances where in oil and gas industry, downstream entities can go offline, causing the safety systems on the upstream entities to react on a frequency of sometimes greater than once a year. This puts a high demand rate and also increases the potential for hazards. We have the requirement for proof test intervals. Proof test intervals are determined when you do SIL verification calcs. A SIL verification calc will use a testing frequency to come up with the probability of failure on demand for the safety instrumented function. So that required proof test interval is going to be something that's going to be pulled out of the SIL verification calcs. The response time requirements for the SIS to bring the process to a safe state. Possibly it's a fuel gas system and some NFPA requirements that say that the gas valves must go from the full open to the full closed position within a 1 second period of time. That would be the response requirements. The safety integrity level and mode of operation, demand and continuous for each safety instrumented function. Somewhere in the hazard analysis, process hazard analysis, a layer of protection was done, and it was determined that there was needed mitigation, or there's some orders of magnitude of risk reduction that were still remaining, and this was going to be applied to a safety instrumented function. At that point, you would choose a safety integrity level, and then after that, do your SIL verification calcs to make sure that your equipment met it. This information needs to be included. A description of the SIS process measurements and their trip points. Well, that's, is it a high pressure? It's a pressure measurement, and the trip point, where you have determined your process is out of control and you need to take the safety action. A description of an SIS process output actions and the criteria for successful operation. Again, with the fuel gas systems, that could be a specialized valve for tight shutoff with a very fast closing time. The functional relationship between process inputs and outputs, including logic, mathematical functions, any required permissives. Again, on the fuel gas system, that low pressure transmitter might be in a position to where until you actually open the valves, the low pressure transmitter isn't seeing any pressure at all. Therefore, there may be a required permissive or a short period of time on which that transmitter doesn't take its action until the fuel gas is actually into the line and the transmitter can sense that it is above the low pressure requirements. Requirements for manual shutdown. Things like NFPA will require that even if you have a logic solver, your sensors and your final elements, your valves, that there needs to be a manual means at which a person can intervene and cause everything to go to the safe state without the use of the safety instrumented system. This could be as simple as a master control valve, or master control relay in the burner management system. We have requirements relating to energize or de-energize to trip, and the associated requirements that would follow, especially for the energized, potentially circuit monitoring and other things that prove that your system is going to be able to take its action when it's demanded to. The requirements for resetting the safety instrumented system after a shutdown. You certainly don't want things to just come in and start up automatically when process requirements are back, or process variables are back within the control boundaries. You want the operation to take the action and say, I want to start it back up. So is it a soft push button, a hard push button, or is it a manual solenoid valve that must be latched in the field? These are the types of things that reflect the resetting of the SIS after a shutdown. Maximum allowable spurious trip rate, and that is that the frequency at which it shuts down when you don't want it to. Certain processes can be shut down and started right back up. Other processes, when they come down, can be very difficult to start back up. This is the type of scenario where you don't want it to spuriously trip as your predominant 2 out of 3 pressure transmitters or temperature transmitters, and a 2 out of 3 vote, or a 2 out of 2, something that will negate that spurious tripping. Failure modes and desired response of the S, alarms, automatic shutdowns. So if you have a failure in the SIS, failure of a transmitter, automatic shutdowns, failure modes, these are the types of things that need to be considered. Any special requirements related to the procedures for starting up and restarting the SIS. Is there anything that has to be taken into consideration that it needs to be documented? All interfaces between the SIS and other systems. Good documentation as to how the SIS is looked at via possibly the basic process control system, operators, lights panels, alarm panels, etc. A description of the modes of operation of the plant and identification of the safety instrumented functions required to operate within each mode. There's a lot of continuous process plants out there that have big safety systems. The most hazardous time of that process plant is usually during the startup or the shutdown, because the systems are designed, especially in past, to look only at the continuous process mode. And with this, we need to be very scrutinizing of what's going to happen and any special requirements of safety instrumented functions so that they can operate correctly within each mode of the operation of the plant. The application software requirements, this is talking about the software, and this is listed in 12.2.2 of IEC 61511 Part 1. Requirements for overrides, inhibits, bypasses, and including how they will be cleared. This is in reference to bypasses, such as you have the 2 out of 3 transmitters, and one of them is in a fault mode. You still have a potential 1 out of 2 vote to trip, but you want to put that one into bypass so that you can effectively repair the transmitter online. Other times bypasses will come in handy is when you're doing full functional testing, that functional testing that's required to make sure that you meet your SIL targets at some type of frequency of testing interval. This information needs to be included. specification of any action necessary to achieve or maintain a safe state in the event of faults being detected in the SIS. And that is, if your transmitters fail, what's the necessary action? And any actions, such actions shall be determined taking account of all relevant human factors. Mean time to repair. You have an SIS out there, it's working fine, and all of a sudden one of your transmitters goes bad. You put it in bypass. You got a guy standing there, and he's monitoring the pressure gauge, and he's also got the shutdown button right there by him for this fired heater. And so now we need to say, well, how long is this guy going to have to stand out there? Is he going to be there for 2 weeks? No, there's an account for travel time, location, spares, inventory, etc. that need to be looked at. The identification of a dangerous combinations of output states of the SIS that need to be avoided. This is looking at the way things, your logic and your cause and effects diagram to make sure you identify that there's no hazards with the way the SIS has been programmed. The extremes of all the environmental conditions, and I'm not going to cover all these, but this include temperature, humidity. You don't want to put your logic controller in an exposed environment to where corrosion and erosion could take place. All of these things need to be looked at and documented. Identification of normal and abnormal modes, and this is again talking about startup, shutdown, maintenance, calibration, repair. And lastly, the definition of the requirements for any safety instrumented functions that need to survive a major accident event. How long does a valve need to remain operational in the event of a fire? Things of this nature. So in the development of an SRS, all of the data generated during the analysis phase of the safety life cycle is required. This includes process information, the potential hazards from the PHA, maybe regulatory requirements from the NFPA for boilers, list of all the safety instrumented functions, and for each safety instrumented function, the required risk reduction or safety integrity level and the related risk analysis information is also required. In IEC 60, ISA 84, IEC 61511 Part 1, this item is a description of all the safety instrumented functions necessary to achieve the required functional safety. This can be referred to as an instrumented protective function list, which can be comprised of all safety instrumented functions, equipment protective functions, and manual protective functions. So here's an example of an IPF list. We have a fired heater boiler here, and we have 3 safety instrumented functions. We have a low flow, we have a high fuel gas pressure, and we have a low fuel gas pressure. They've been identified as safety instrumented functions. During some SIL selection process, a SIL A was chosen for item 1, a SIL 1 for item 2, and a SIL 2 for item 3. Process safety time for the first safety instrumented function shows to be less than 60 seconds. For the 2 and 3, less than 3 seconds. The demand mode of the SIS is low, so we don't expect to see a demand on that safety function greater than the testing interval at which the function is given its full functional test. We have the input, we have the sensor tag names and information, whether it's the low trip or the high trip. Sensor voting, first one there is a 1 out of 1. The second SIF is a 1 out of 2, and the third SIF again is a 1 out of 2. Location logic solver, in this particular scenario, was defined as a SIL 3 certified logic solver. Some third party, TUV, Exida, or somebody else has defined the certificate for this piece of equipment, and it's a certified logic solver. On the outputs, we define the final element interface, which is the solenoid valve that is working with the actual fuel gas valve. Here they're defined as quick exhaust solenoid valves. The final elements are defined as two valves, UV 301A and B, and the final element voting. We also have the reset type, which says it's a manually latching solenoid. So if those valves go closed and we get permission back from the SIS, the reset only takes place when the operator walks out to the field and pulls the lever on the solenoid and latches it back into place. So we have that instrument of protective function list, and it addresses a lot of the items in 10.3. So item number 1, a description of all the safety instrumented functions necessary to achieve the required functional safety. Well, here I'm just using a simple example of one of the safety instrumented functions, but if we had the entire list below us, such as the 3 before, or a larger list of 10 safety functions or 20, that instrument of protective function list would address the need of 61.511 Part 1, 10.1. And in 10.3, a definition of the safe state of the process for each identified safety instrumented function. Here it says that we close the gas valves, puts us in a safe state. Item 5, the assumed sources of demand and demand rate of the safety instrumented function. The demand rate, the demand rate. Demand is low, which is it's red, it's redundant to 2 different things here. The response time requirements for the SIS to bring the process to a safe state. Process safety time is less than 3 seconds. The safety integrity level and mode of operation demand are continuous for each safety function. That's our IPF type, our selected SIL, SIL 1, and again the demand mode, it's a demand of low. We address number 9, a description of the SIS process measurement and their trip points. So in the IPF it says the list has the pressure transmitter 301AB low trip at 3 psig. And in item 11, the functional relationship between process inputs and outputs, including logic. That's in the uncolored areas, plus everything else in line with the safety instrumented function. It says that we have a sensor, the voting's 1 out of 2, it goes into the logic solver. We have final element interfaces, we have the final elements, and the final element voting is a 1 out of 2. Number 13, requirements related to energize or de-energize to trip. Again, in the IPF description, low pressure de-energizes solenoid valves closing double block fuel gas valves. And number 14, requirements for resetting the SIS after a shutdown. The reset type is a manual latching solenoid. So this IPF list addresses a good portion of the requirements of those 27 different items. So let's look at item 2. It's the requirement to identify and take account of common cause failures. So if an input group has 3 transmitters connected to the same sensing element in a 2 out of 3 voting arrangement, a plug sensor line would cause all 3 transmitters to fail. So in this scenario, we can go to IEC 61508 Part 6, Annex D, and it contains the methods for determining the beta factor for common cause failures of field devices and logic solvers. There's a lot of calculations and a lot of yes-no answering to a bunch of questions. And this particular table is built into a lot of different software programs, hazard analysis, fault trees, and etc., so that it will automatically calculate the beta once you answer the proper questions. So again, in 61.511 Part 1, 10.3.1, line item 10, a description of the SIS process outputs actions and the criteria for successful operation. For example, it says requirements for tight shutoff valves. So in your SRS report, in the definitions of your final elements, the documentation should follow something like this. Final elements shall be fast acting, less than 2 seconds, and be tight shutoff fuel gas valves. The final elements shall be independent from those used by the basic process control system. Each final element or final element interface device, e.g. interposing relay or solenoid valve, shall be individually hardwired to an independent output on the SIS logic solver. No intrinsic barriers, isolators, repeaters, or other equipment shall be connected in the final element loop of any safety instrumented function. Final elements shall not incorporate a means of bypass. No digital bus communications, HART, field bus, etc. shall be used for final elements that are part of a safety instrumented function. All final elements connected to the SIS logic solver shall be independently and individually hardwired as digital outputs. Digital bus communications shall be permitted for diagnostics and alarming and shall follow the implementation guideline in the manufacturer's installation, operation, safety, and programming manuals for the SIS logic solver. So what happens is you write a specification, but you don't put all the finite details about the final elements that were just done here. And somebody says, well, you know what, that basic process that we need double block valves, but yet that basic process control valve for the fuel gas flow, we'll put a solenoid on it and cause it to close. So now we have two. Well, it might not be fast acting, so that negates it, and the final element shall be independent from those used in basic process control. Can't use it. So we've defined something that makes it very stringent guidelines for the implementation of the actual construction and building of the SIS. No intrinsic barriers, isolators, or repeaters. You go in and you specify we need 2 pressure transmitters coming into the logic solver, and we go out and we go to a valve. And the whole system is built, SIL verification calculations have been done, and then all of a sudden you find out that the standard operating practices of this one particular place are that they put intrinsic barriers on all of their equipment. So all of your SIL verification calcs are now out the window because they added another piece of equipment in series with the logic solver and the transmitter, and it hasn't been taken into account. So here we make the statement you can't do it, and if we make the statement that you can do it, it will say just that, and we will have to include those pieces of equipment in the SIL verification calcs. Final elements shall not incorporate a means of bypass, and I have seen major players in industry actually put bypasses around their safety shutoff valves for whatever reason, which is an absolute no-no, because even the partial opening of that valve totally negates the potential for the safety function to work. You have a lot of documents. You got the process hazards analysis. You got the layer of protection analysis. You got the safety instrumented function definitions, the safety integrity level selection, the SIS equipment specifications, the safety integrity level verification calculations. How do you get it all together? A good worksheet is a good way to do it. You might have 5 documents, you might have 25 documents. You take it and you put it into literally put it into Excel. You put your relevant numbers from your 61511 Part 1, Clause 10. And you list them all out, and then you put your text in. So here we're talking about big refinery, and I'll look all the way down 10.2.1. Relevant, it's very relevant. The safety requirements shall be derived from the allocation of safety instrumented functions, etc. The requirement and the expectation. The clause requires that the safety requirements be written in a manner that correlates with the SIF allocation, etc. And the findings. There is an excellent correlation between the SIF definitions through the various documents. It is easy to find relevant information pertaining to each safety instrumented function. The references, and these are the documents that you're referencing. The Big Refinery SIS Design Report with SIL Verification Calcs. The Big Refinery SIL Selection and Layer of Protection Report. The Big Refinery Safety Requirements Specification. So you can actually take that reference and be more exact with it and point it right to a page number or a finding number or a clause number in the report so that anybody that's looking for this information can drill down right to it and get it. These requirements, 10.3.1, shall be sufficient to design the SIS and shall include the following. Big refinery safety standard specification, requirement specification shall include all of the attributes. And that is everything below. That's the 10.3.1.1, 10.3.1.2, the 27 that were defined earlier. And then where the document is located, the name of the document, the part in the document, and whether it is it good? So you're doing your own review and your own findings, and you're saying, hey, is this good? Is it excellent? Is it acceptable? Is it something missing? And it's where the missing part comes in, is that you need to go back and you need to either get the documentation and get it up to par, or go through that portion of the safety life cycle and redo it so that you have something that can be referred to, that's easily defined and can be brought into the assessment here and judged to be whether it's in good, excellent, or poor condition. So as a wrap-up, a number of documents are required. There is no required method of putting it all together. Nobody out there has done anything. There's no software that kind of pulls it all together. It's really left up to each individual user. But the key to remember is that the requirements should be expressed and structured in such a way that they're clear, precise, verifiable, maintainable, feasible, and written to aid comprehension by those who are likely to utilize the information at any phase of the life cycle. So it's kind of up to y'all to put it together. I find that the worksheet is a great way identifying each and every one of the points in 10.3 and then pointing to the relevant document that contains that information. That will allow you at any point in time to get any of the information of the SRS at your fingertips in an expedient period in time. So that about wraps it up here. Again, my name was Christopher Weil from Kenexis Consulting, and this has been the webinar on SRS.